Hey friends, welcome to the YouTube channel All About Electronics. So in the last video of filter design, we had seen that how to design the low pass as well as the high pass Butterworth filters using the Salunkey filter topology. So in that video, we had seen that this Butterworth filter is having a flat pass band and the roll-off of this filter is at the rate of 20 dB per decade. That means suppose if you are designing the fourth order filter, then the roll-off that you will get with this filter will be at the rate of 80 dB per decade. So now in this video we will see how to design the low pass as well as the high pass Chebyshev filters using the Salunkey filter topology. So this Chebyshev filter provides the faster roll-off rate compared to the Butterworth filter. But in this Chebyshev filter you will see some sort of ripples in the pass band. So now suppose if we want to design the Chebyshev filter, then we need to know some parameters about this filter design. So let us see those parameters one by one. So the first parameter about this design is the passband ripple, that is the maximum allowable ripple in the passband. Now the second parameter of the design is the passband cutoff frequency. So now the filters which is having a flat passband, like in the case of Butterworth filter, the cutoff frequency is defined as the frequency where the output is 0.707 times the maximum value, or it is also known as the 3 dB frequency. But for the filters which is having a ripple in the passband, the cutoff frequency is defined as the frequency beyond which you will not see any kind of ripple. So for this filter, this frequency is known as the passband cutoff frequency, that is omega p. So as you can see here, beyond this cutoff frequency you will see the monotonic response of this filter, and below these frequencies you will see the ripple in the passband. So apart from these two parameters, the remaining two parameters are stop band cutoff frequency and stop band attenuation. So the stop band cutoff frequency is the frequency beyond which the stop band of that filter will start, and the stop band attenuation defines the minimum amount of attenuation that you will get in the stop band. So suppose let us say for this filter, this frequency defines the stop band cutoff frequency. Let us say that is a omega s, and let us assume that in this stop band minimum amount of attenuation that is being provided by the filter is 60 dB. So these two parameters defines that if you go beyond this stop band cutoff frequency, then you will get at least 60 dB of attenuation. So this region is known as the stop band of this particular filter. So now to design the Chebyshev filter for our requirement, we should know all these four parameters. So now generally these type of filters are designed using the filter tables. So here are the some of the parameters which you will find in the filter table. So in this video we will learn what are these different parameters and what is the significance of all these parameters, and using these parameters how we can design our filter. Now before we understand this filter table, let us see some mathematics which is involved with this Chebyshev filter. Now for the filter design, this mathematics is not at all required, but to get a better idea of this filter, let us see some mathematics which is involved with this filter. So now here as you can see, here is the normalized response of this Chebyshev filter. So the maximum value represents the value 1. So now this type of response mathematically can be represented by this equation, where here this epsilon represents the ripple factor of this filter. That means the amount of ripple which you see in the response, and this term represents the Chebyshev polynomial for the nth order. And here this polynomial is also normalized with respect to cutoff frequency or a passband frequency omega p. So whenever this term is less than 1, that means frequencies which are less than omega p, the function can be represented by this equation, and as you can see it is having a periodic behavior. And the frequencies which are beyond this passband cutoff frequency, the expression can be represented by this expression. And as you can see, as you go beyond this cutoff frequency omega p, you will see the monotonic behavior. So now as we have a basic idea about this Chebyshev filter response, now let us see how to design this Chebyshev filter by taking one example. So in this example we have given that we have to design the low pass Chebyshev filter which provides the maximum gain of 5 dB, which is having a passband ripple of 0.5 dB, and the cutoff frequency of this filter is 2500 radian per second. Apart from that, we have been given the stop band frequency, that is 12.5 kilo radian per second, and the stop band attenuation which is required for this filter is 30 dB or more. So as you can see here, we have been given the 4 different parameters which are required for the filter design. So now from these 4 parameters, first of all, we should decide what should be the order of the filter for our design, and that can be decided by this expression, where here AS represents the stop band attenuation, AP represents the passband ripple, omega S is the stop band cutoff frequency, and omega P is the passband cutoff frequency. So we have all these 4 parameters. So let us put all these 4 parameters inside this equation and let us find the order of the filter for this design. So if we put all these values and solve the equation, then we will get value of n as 2.267. Now here the value of n should be integer. So the value of n should be equal to 3. That means for this design, we require the third order of Chebyshev filter. So now once we know the order of the filter, then by using the mathematical equations, we can find the transfer function of this filter, and through that we can design the filter. But the same thing can be done just by using the filter table. So here we will solve this problem using the both the methods. That means by using the equations and then using the filter table, and at the end we will see that we will get the same result. So let us first of all solve this problem by using the mathematical equations. So here I will quickly go through the mathematical equations. So wherever you feel, you can pause the video and you can try to get those values by yourself. So the next step is to get the transfer function of that particular filter. And to get the transfer function, we need to first of all find the different poles of this particular filter. And these poles can be found out by using this expression, where this phi is nothing but 1 by n sine hyperbolic inverse 1 over epsilon, where here n represents the order of the filter, and the value of epsilon can be found by using this expression, while theta can be represented by this expression, where the value of k is from 1 to n. So now for our design, the value of n is 3. So first you need to get the value of this epsilon, and from that try to get the value of this phi. And once you know the value of phi, then find the value of these different thetas. And if you put the values of this phi and theta inside this equation, then you will get the 3 different number of poles. So here is the value of epsilon and different values of poles. So try to get those values by yourself by putting the value of this phi and theta inside this equation. And from these poles, we will get this transfer function, where here this h0 represents the value of this transfer function at omega is equal to 0. So when we put s is equal to 0, then we will get the value of this h0. And we know that when the order of the filter n is odd, that means n is equal to 3, then at omega is equal to 0, the value of this transfer function will be equal to 1. So that means h of 0 will be equal to 1. And through that we will get the value of h0 as 0.715. So in this way we will get a transfer function of our filter. Now apart from this, in this example we have been given that we are providing a 5 dB of gain to this filter. Now this 5 dB is nothing but 10 to the power of 0.25, which you can get by equating it with 20 log of A. So from this you will get the value of A as 10 to the power of 0.25, that is nothing but 1.7783. So we also need to multiply this expression by this factor. So now our overall expression will look like this. So this is the transfer function of our filter, and using this transfer function we can design our filter. So now if you see here, this filter consists of 2 stages. The one is the second order stage and another is the first order stage. So by combining these 2 stages we can design this filter. Now if you know, in the last video we had seen that the transfer function of second order filter can be given by this expression. So if we compare that expression with this term, then we can get the value of q and omega. So if we compare these expressions, then the value of omega n square is nothing but 1.1424. That means the value of omega n will be equal to 1.0688 radian per second. And similarly, if we compare this omega n by q with this value, then we can get the value of q as 1.7063. Similarly, if you compare this first order stage with this expression, then you will get 0.6264 divided by s plus 0.6264. That means for this first order filter, the cutoff frequency omega n will be equal to 0.6264. So these are the parameters which are required to design our silent key filter. And if you look these parameters inside this filter table, then indeed you will find that the values are exactly matching. Like here you can see for the third order filter, the first section is the second order filter and the second section is the first order filter. So here this F0 represents the scaling factor of this filter. Now here this filter table is designed for the cutoff frequency of 1 radian per second. So this scaling factor basically represents the amount by which we should scale our cutoff frequency of that particular section. So as you can see here, for this first stage, the cutoff frequency is 1.0688. And if you see here, exactly we got that value. Similarly, if you see the value of q for that section, that is equal to 1.7061. And here this alpha is nothing but 1 over q. And similarly for the second section, the cutoff frequency is 0.6265. And exactly we got that value. So in this way, if you know the order of the filter, then using this filter table, we can directly get that transfer function. And we do not require to go through that all the mathematical steps. So now let us quickly see using this filter table how we can get that transfer function. So now let us quickly see using this filter table how we can directly get that transfer function. So the following are the scaling factor for the two sections. Now the quality factor for that second order section is 1.7061. That is 1.7061. So now we know that the second order transfer function can be given by the expression k into omega n square divided by s square plus omega n by q into s plus omega n square. Now here the value of omega n will be equal to 1.0688 and the value of q will be 1.7061. And if we put all these values inside this equation, then we will get the expression that is 1.1424 divided by s square plus 0.6264s plus 1.1424, which is the same expression that we have got by using the mathematical equations. Similarly for the first order stage, if we compare this equation with the transfer function omega n divided by s plus omega n, then we can write it as a 0.6264 divided by s plus 0.6264. And if we multiply these two expressions, then we get the same transfer function that we have got using the mathematical equations. So in this way, using this filter table, we can very easily get this transfer function. So now once we know the transfer function of that filter, then the next step is to decide the values of these R and C's for the given filter. So our third order filter should look like this, which consists of second order silent key filter followed by the first order low pass filter. So let us decide the values of these R and C's from the transfer function. And first let us take the case of this second order section. So for this section, let us decide the values of this R and C's. And in the last video, we had seen that the transfer function of this silent key filter topology can be given by this expression. So in the last video, we had seen that when the value of R1 is equal to R2 is equal to R and C1 is equal to C2 is equal to C, then the value of Q can be given by the expression 1 over 3 minus K, where K represents the gain of this filter. So just by adjusting the gain, we can get the desired value of Q. Now if you closely see this example, in this example we have been also asked to get a gain of 5 dB, which corresponds to the value 1.77. And for this design, we have just found out that the value of Q should be equal to 1.7063. Now if you put the value of Q that is equal to 1.7063, then the value of gain will be more than 1.77. So in this particular example, we will not go through this procedure. Rather, we will go through the different procedure. But suppose if you are not given the value of gain, then you can follow the same procedure which we have followed in the Butterworth filter design. So here what we will do, instead of using this feedback gain, we will use the unity gain silent key filter. So the value of k will be equal to 1. And when the value of k is equal to 1, then the q can be given by the expression under root r1 r2 c1 c2 divided by r1 c2 plus r2 into c2. Now here we will take r1 is equal to r2 is equal to r, and we will choose different values of c1 and c2. So now in this expression, when we will take r1 is equal to r2 is equal to r, then the value of q will be equal to 0.5 under root c1 by c2. So now here, just by adjusting the value of c1 and c2, we can get the desired value of q. And the cutoff frequency omega can be given by the expression 1 divided by r into under root c1 into c2. So in this way, just by adjusting the value of c1, c2 and r, we can get the value of q as well as the omega for our given example. So now so far, we have considered this transfer function for the frequency that is equal to 1 radian per second. But in our design, we require the cutoff frequency omega c or omega p that is equal to 2500 radian per second. So now to get the transfer function, simply replace s by s divided by 2500, and replacing that you will get the transfer function for the cutoff frequency of 2500. So now here the cutoff frequency omega will be equal to 2500 into the scaling factor that is equal to 1.0688, and that value will come out as 2670 radian per second. So this will be the cutoff frequency of our filter design. Let us also assume that the value of R for this case is 10 kilo ohm. So if we put this value, then we will get under root C1 into C2 as 37.4 nanofarad. And let us say this is our expression number 1. Likewise, we know the value of Q that is equal to 1.7063. So now if we put this value in this equation, then we will get under root C1 by C2 as 3.4126. And let us say this is our equation number 2. So by multiplying this equation 1 and 2, we will get C1 as 127.6 nanofarad. And if we put this value of C1 in either of these equation, then we will get the value of C2 as approximately equal to 11 nanofarad. And we have already assumed the value of R1 and R2 as 10 kilo ohm. So in this way, we have found the value of C1, C2 and R1, R2. So in this way, we have designed the first section of this filter. Now let us similarly design the second section of this filter. Now here the gain that is required in our case is 1.77. That is 1 plus R7 by R6 should be equal to 1.77. Or we can say that R7 by R6 should be equal to 0.77. So if we assume the value of R6 as 10 kilo ohm, then the value of R7 should be equal to 7.7 kilo ohm. So these two values will define the gain of this particular filter. Now let us decide the value of R5 and C5. Now for the second section, we know that the cutoff frequency omega p will be equal to 0.6264. And let us multiply this cutoff frequency with our desired cutoff frequency, that is 2500 radian per second. And by multiplying, we will get value as 1566 radian per second. So this will be the cutoff frequency of that second section. And this cutoff frequency is given by 1 over RC. So now let us assume the value of C as 0.1 microfarad. And if we put the value of C as 0.1 microfarad, then we will get the value of R as 6.38 kilo ohm. So in this way, we have got the value of R5 as 6.38 kilo ohm and value of C5 as 0.1 microfarad. So in this way, we have decided all the values of R and C's for this particular design. So in this way, by using this filter table, we can design any order of Chebyshev filter. Now these filter tables are defined for the different values of passband ripple. Like here, this filter table is defined for the passband ripple of 0.5 dB, and likewise we can have a different filter tables for the different values of passband ripple. So in the description, I will provide the different filter tables for the different values of passband ripple. Now so far, whatever discussion that has been carried out, that was for the low pass filter design. Now similarly, let us see how to design the Chebyshev high pass filter. Now let us say we want to design the high pass filter which is having the same cutoff frequency that is equal to 2500 radian per second, and it is having the same roll off rate that was for the low pass filter. So simply by replacing S by 1 by S, we can transform any low pass filter into the high pass filter which is having the same cutoff frequency. So now in this expression, if you replace this S by 1 over S, then you will get the high pass filter which is having a cutoff frequency of 1 radian per second. And after that, if you replace this S by S divided by 2500, then you will get the transfer function for the high pass filter which is having a cutoff frequency of 2500 radian per second. So try to do it by yourself and do let me know the new values of this Q and the frequency scaling factor F0. And once you get the transfer function, then using this Salenki filter topology, you can decide the value of R and C's. So try to get the value of R and C's for the high pass filter and do let me know your design values. And in the last video, we had seen that the transfer function for the high pass filter can be given by this expression. So using this expression, you can find the values of R and C's. So this is all about the Chebyshev low pass as well as the high pass filter design. So I hope in this video, you understood how to design the low pass as well as the high pass Chebyshev filters. So if you have any question or suggestion, do let me know in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.